I'd like to welcome you to the fourth day of this conference and ask you all to take a seat. It is a great pleasure to introduce the Shannon Lecture today by Professor Rudolf Ahlswede, Professor Emeritus of Bielefeld University and 2006 Claude E. Shannon Award winner. Since I had the opportunity to say a few words about him at the awards luncheon on Tuesday, my introduction today can be brief. Indeed, little introduction to him is needed in any case, except perhaps to the newest members of the information theory community. Professor Ahlswede received his doctorate from Göttingen, has held professorships at Ohio State and Bielefeld, and visiting positions at a number of other institutions. The Shannon Award is for consistent and profound contributions to information theory. He's spent his career making such contributions, and for this work, he has received a number of awards, including 2 information theory paper awards. He's expanded the boundaries of information theory in a number of ways. Even so, much remains to be done, and I'm very glad to hear that he is contemplating a general theory and look forward to his talk toward a general theory of information transfer. Please join me in welcoming the winner of the 2006 Claude E. Shannon Award, Professor Rudolf Ahlswede.
Thank you very much. It was nice. Thank the President for this compact introduction, which gives me also time for the lecture. So, you know the title. Now, this is a very great day for me, because for the first time in my life, I speak with an LCD. Also for the first time in my life, I give a Shannon lecture, whereas others have practiced this earlier. So for the 2 reasons, my lecture has to fail with probability 1. Now, I can give the lectures in 3 forms. The first form is there. It's 3 lines, 5 syllables, 7 syllables, 5 syllables. That's called a haiku in Japan, a form of poetry. More than restoring strings of symbols transmitted, what Shannon taught us means transfer today. Now, I never met Shannon in person. This gives me the possibility to communicate with his spirit. You may say that's a not fair constellation, but on the other hand, this gives me also a chance in the light of this great man. And the second form is here now. Has 3 parts: probabilistic models, transmission via discrete man and shell, but also called Shannon Theory. It's on this slide already. The theory of identification, which I did in the late 80s with the help of Gunter Dück, including feedback. And then it turns out that in this theory, a certain number plays a big role, which originally I called mystery number, because it was a mystery that it always came up. But later it was called common randomness capacity. And I formulated a principle. Now, here things grow exponential in the block length. The code size grows exponential in the block length. Here it grows double exponential. But common randomness again grows exponential. I speak of first order, of second order. And so the principle is first order common randomness capacity equals second order identification capacity. There will be many, many results which we obtained following this principle with several co-authors. Then I highlight 2 results, one for Kova's broadcast channel and one for Weiner's wiretap channel. And then I very briefly indicate a more general theory of transfer, which includes those two theories as extremal cases, but it covers many others. Then I jump to quantum theory. I assume that most of you don't know quantum information. Nevertheless, I dare to give some hints as to methods, which classical methods work, which don't work. And that is very fascinating. So this is definitely more than just applying classical things, etc., etc. Also, the contact with physicists is very, very important there. So this is a great enlargement of the information theory, which was not touched upon by Shannon in those days. Finally, I go from channel coding to source coding. You can also formulate identification for source coding. And then, in this context, I fairly recently discovered a new entropy, which I call identification entropy. Then there are combinatorial models. For one, a very simple memory device of updating leads to the concept of anticodes. You know codes? The distance is bigger than something. Anticodes, the distance is less than something, which we completely characterized. It's very amazing. So the dual to coding was completely characterized together with Khatchatrian. And if you have constant weight, this is exactly the classical problem by Erdős-Corrado, which was unsolved for more than half a century, and we completely solved. Then I turn to network coding. You have heard of it. I call it Shannon-Smith theory, because Shannon wrote a paper with Elias and Feinstein on flows, developing algorithms, but he always used flows which satisfy Kirchhoff's law. So what comes into a node can only go out as a balance. He did consider information flows, where you can violate the law, because you can copy. And the engineering, the communication, no, the computation community has done a lot of this copying. But they didn't realize that this is still suboptimal. You can use coding, and that's what's called network coding nowadays. And I will discuss many, many more things about this. Then there's some work with Spinsker and Basaligo, where we worked in the 90s for 10 years. We had some ideas about it, and we made a gentleman agreement. We continue working and publish everything together until the problem is settled. We almost settled it. And Mark wrote it down a year before he passed away, and I will give the result. Then I speak about search. That either you speak about search or error-correcting codes with feedback. It's absolutely equivalent. And one community doesn't know about the other. Berlekamp used the formulation error-correcting codes with feedback. Reni introduced it somewhat earlier as the so-called Koch-Bar game, which was very popular in Jewish communities in Budapest. And it's the following. You have a ground set, and there's one element in it which you search. And the way you search is you choose a subset, and then you get the answer, it's in there or it's not in there. It's a very simple search problem. And if you do it right, you can do with log cardinality of the ground set many tests. But Reni also introduced liars. And then it is absolutely equivalent to the problem considered by Berlekamp. Ulam stated this problem many years later, but he got most of the credit of this. So now Berlekamp thesis 2. 2 weeks ago, I was in Victoria, and Christian Deppe, who is one of our co-authors on our work, presented the work, and great Berlekamp was sitting there, and I saw how he took out his notebook. I said, aha! And after the lecture, he came and said, can you give me the paper? It's very interesting. So he did the binary case. They couldn't do the query. We do the query completely with a new method from which he can also do his case. And that's why I call it Berlekamp's thesis part 2, because he did it in his 64 thesis. So it's 40 years old. And I think he's not here, so I'm thinking he's writing already the second part of the thesis. Reni-Smith theorem concerns the situation where there is no liar. But I told you, if you do it right, tests have cardinality essentially half. But he asked, what if the cardinality is restricted? What is then best? And I found the best answer, and entropy comes in. And this great man, who many, many years worked on entropy, didn't even ask whether entropy is the right parameter. And that's why I call it Randomness theorem. Finally, I talk about combination of combinatorial and probabilistic models. Like if you have a correlated source, you know the distribution of two components. What if you know only the conditional probabilities? You know less and do source coding. And there's a whole world of models between combinatorial, which is usually studied in algebraic coding and combinatorial coding, and probabilistic, which is usually called Shannon Theory. There's a whole world, and there was one problem by Gallaghers, which I settled, which was one of the motives for me to write a long paper 25 years ago about many such models, but very little impact and very little follow-up so far. Finally, I will mention some perspectives, protocol information beyond information theory, a concept of solution, so some recent in a connection of information theory and number theory by Tau, questions to Shannon, and you will see. So this is the second lecture I gave, so you roughly know what I'm talking about. And now I have to go to the work, that means to the details here. And so I start out with Shannon's classical result. So be precise in language. What Shannon did, I call transmission. No other word, transmission. And what he does is, he answers what is the actual message. The receiver wants to know what is the actual message. And he wants to answer it correctly with probability close to 1. We use a discrete memory channel, inputs alphabet X, output Y, stochastic matrix. Shannon had the idea to code at the time where von Neumann was still repeating. The code, block length n, size n, epsilon error probability. Set of pairs, the ui's in the input space, the di's in the output space, and decoding sets disjoint, of course, and error probability smaller than epsilon, and you maximize the size. And in this 48 paper, Shannon stated the theorem, which has many other formulations in this form. The number grows exponential, take logarithm, divide by n. It converges independent of epsilon to a constant. And this constant can be expressed in terms of entropy and conditional entropy difference maximized over all x. That is Shannon's famous theorem, you all know. And now we go to identification. The difference here is the general model absolutely the same. The difference is the question is different. Is the actual message I, the receiver asks? But the sender doesn't know for which I he cares. Could be anyone. And the encoding has to be done in such a way that all those questions are answered correctly with probability close to 1. That's a different question. But it takes people time to even understand the difference. In this case, randomization helps a great deal. So we encode not by word, but by probability distributions on the input space. Decoding sets need not be disjoint. And we have error probabilities of two kinds. One, I is there, but we reject it. The other one, we accept I, even though J is there. So there are two error probabilities, like in hypothesis testing, but now you have it for any two pairs kind of hypothesis testing. And you define a code like this as usual, having some parameters. And now it turns out that the optimum, that this number now, this identification size, code size, grows double exponential. You take log, and then a constant comes in. It turns out that this constant is again Shannon's capacity. So it appears in a constant in double exponential. Now we turn to feedback. There are two versions. The encoder has possibility to randomize, or he doesn't have. If he doesn't have, this is the answer. This is the optimal, this is the capacity. If he can, this is the answer. Now you look at those results. You notice, of course, feedback increases. This is bigger than capacity, whereas classically, for a noiseless channel, Shannon proved it doesn't. So here it increases. Also, noise can increase identification. If you would have here a 0-1 matrix, it would be 0. So second order would be 0. So noise helps. And it's similar to game theory where mixed strategies help. So the phenomenon that noise helps is very important also for nature, for Darwinism, etc. Now we got another idea. So if you look at those quantities, you can view them as some kind of common randomness rates. The sender sends letter XXX all the time. This creates a process at the output, Y1, Y2, Yn. Having feedback, the sender also knows it. So both know this output process, and its mean entropy, if you choose X in an optimal way, is this. You can play the same game if you randomize, and you can replace X by a probability distribution of input letters. And this way, they produce a random experiment to which they have access, sender and receiver. And the observation was then later one could use this. Whenever you have quantum randomness, there's a lemma which says how to go from there to identification by, I call it the square root n trick. And from there, I formulate the principle that there's always this connection. Now, where is the common randomness there? Well, if you use a channel, ordinary channel, and the task is sender and receiver shall build up a common random experiment, what can you do? The best you can do, you take a good transmission code, average over it, then you have a random experiment, send it, decoder up to a little error knows it, and there's no other way to establish more common randomness. So the randomness capacity equals transmission capacity. And from now on, I speak about three capacities: Shannon's transmission, common randomness capacity, and second order identification capacity. So keep in mind those three quantities. And they need not be equal. So now this theory also created some other problem. If you want to prove converse for identification, you know we randomize. You have the problem, you have any probability distribution on the input, the channel produces an output, and you want to produce this output distribution with an input distribution which lives on as small as possible set with uniform distribution. Because this way you can count. Here you have continuously many distributions, you cannot count, you cannot derive anything. And this is output distribution, which has been also studied a great deal by, and forwarded by Verdu and Han. Now, I draw again attention, what the great man says. The fundamental problem of computation is that of reproducing at one point, either exactly or approximately, a message selected at another point. Now, identification does not fall under this. We do not reproduce the message. And so I ask, what is information? How do we measure information? Are those the Cn bits in Shannon's fundamental theorem? Are those the log Cn bits in our theory for identification? It depends on the model. And the basis of Shannon's theory, thinking seriously, not turbo fountains, but thinking about basis of information theory. The basis of information theory needs to be enlarged. We are going beyond Shannon, and that's why I dare the title towards the general theory of information transfer. Now, originally talked about mystery numbers with feedback, and here it's defined. Don't bother about the details. It turned out that in multi-user theory, we could solve almost every problem with feedback, whereas for transmissions, almost none of them is solved. And the capacity is always this mystery number. Now, this mystery number is a maximal entropy. It may be computable, or it may not be computable. But whatever it is, it's always the truth. And we also give some formal definition for common randomness. You have to allow a little epsilon deviation for equality to make it right, and so on. And there are two basic papers which I wrote subsequently with Imre Schieser on this. But here's a square root n trick, which is a basic thing. You have m set and m prime set. And you have maps which map m into m prime. Now we define new sets ki by taking the pair of m and its image. This gives us a set chi. So this lives now on the product space. And you define a probability distribution by taking the uniform distribution. Then there's the following lemma. If this m prime is of this order, that's where the square root comes from, so it's much smaller than m, then there exists such a family which is very, very big. It's exponential in m. That's why we get the double exponentiality. It's exponential in m. Of course, all those chi carry power 1, but mutually they intersect by less than epsilon. So they give us the required identification code. In typical explications, the common randomness part is done in block length n. The extension to get identification needs only square root n through very few letters. So now here are the results known insofar. You know, this is Shannon's basic theorem, multiple access. I did 70, 71, capacity region. Now broadcast general still unsolved, Shannon's two-way channel still unsolved. In identification, I know the answer, and very surprising, I know the answer for identification for the broadcast channel, even though we don't know it for transmission. And usually the identification problems are harder. But in this case, I could solve it. And with feedback, discrete channel we know, multiple access generally still unknown, but if I have allowed deterministic encoding only, I can settle it. If I allow randomization, still unsolved. To get the single letterization. Broadcast channel, amazing, dual. Deterministic, we don't know. If you allow randomization, can do it with feedback. And two-way channel, deterministic, we can do it. So this shows you amazing dualities and how rich the influence is also on classical, because if you can do something there, you look there, etc. So this is the situation. I mentioned this just before. Now, there are several co-authors. I don't name them. You can see the names who contributed to this. So it went in several directions. Also, sometimes classical problems could be done by the new method, etc. I want to highlight only two things. One is here. You have the multiple access channel. You allow randomization. And you want to produce an output process of maximal entropy. How do you do it? I don't know how to do it. So yes, you have entropy maximization, whereas in Shannon theory you have mutual information maximization. So, and now comes another pearl, I would call it. We have our channel set up. We want to use it for identification. But I told you, if you have common randomness, it's good. The common randomness doesn't have to come from the system. It could come from the moon. Any process you observe, you could use, and whatever the common randomness capacity is, adds to the identification capacity. So now we get the help in the form of a correlated source, not just a common randomness. There we could use it. No, one observes UN, the other observes YN. How does this help? And we didn't know how to do it. Well, I said there is a principle I have that those quantities. So we turn the problem around and ask for common randomness in the correlated source, helped by the channel. That should give the same quantity. And here we go. It turns out this is exactly the question asked by Gallaghers, or treated by Gallaghers. You want to extract from a correlated source as much common functions which are equal and have a big rate. And the result is, in most cases, this is 0. So for instance, if all probabilities are positive, it's 0. I don't want to go into more details. So how does it relate to the previous one? It's a case where my channel is capacity 0. There's no help coming from the channel. But if I have help, I can solve the problem. So we have the region and I have this. Now also I draw attention. They called it common information. And they were surprised that it is smaller than mutual, much smaller than mutual information. Because the idea was they should give an interpretation of mutual information. But it didn't. It's much smaller. But now we understand it is just a form of common randomness. And now it's well integrated in information theories, whereas earlier it was always a beautiful singularity sitting aside. And Weiner then said, well, the common information should depend on the probabilities and not just on fact being positive or not positive. And he set up another quantity, which I never could warm up, even though it has maybe applications in other directions. But as a common information, I never could warm up with it. And for one thing, it is very, very big. It's bigger than neutral information. Now, having taught this principle, and having gotten all those beautiful results, people always said, is it a principle or is it a theorem? You're a mathematician. Is it a principle? Well, it's a principle. It ought to be true. Well, don't bother me with your epsilons. And someday I had the time during the Serbian war. They kept me for 24 hours, and I took a pencil and paper and tried to prove it. And I came up with a counterexample. So it is not always true, but the exceptions are very pathological. I have a channel, increasing in alphabet, increasing memory, etc., etc. If you have usually IID situation and so on, it is true. So that's the story. And so, but this has a consequence. This is a construction you cannot follow now. But this has a consequence that the theory of common randomness and theory of identification are really separate theories, because people were trying to say it's one theory. That is not the case. Now I come to those two consequences for sequencing system. Here is Kova's broadcast channel, HUD. There's something called the ABC coding theorem. You have separate messages and common messages. And there's a capacity that has been determined. Kova, van der Molen did the one direction, Kerner-Martin did the converse part, and it's described here. This is the region, using those auxiliary random variables, those mark conditions. If you don't know this, you won't understand it now. You just take the message, there is something like this. And now this is our surprising result. For the general broadcast, the set of achievable pairs of second-order rates for identification is given by B, Ty prime union. So how is Ty prime built? From Ty, you add the common rate and the separate. And also the common you keep separate. So you build from those sets. And this way you get the identification rates and also the common randomness capacities. And this is, of course, relevant for cryptography, because common randomness you can interpret as key, common key. And so you produce by a broadcast channel two keys. And we know the optimum. And the other amazing thing is, presently, the only proof I have for this result, for cryptography result, goes via identification. So I go in the double exponential world to get it down on the exponential world. So that is this result. Now I think I have to hurry up a little bit. What is this now? Oh yeah, this is the second part. This is Weiner's wire tape channel. And so this was, sorry. I told you it will go on. This is Weiner's wire tape channel introduced by him, generalized by Schieser Kerner. For identification, it was settled by Zhang and myself. The result is, if you can get through one bit securely in identification, you get the full rate through. And it sounds very simple, but it's hard to prove. But here, in this case, we introduce feedback from the legitimate receiver. The enemy has no access to this feedback. So it's assumed that he manages to get it through this way. So what are the capacities? Transmission capacities, we have bounds. We expect the lower bound to be the truth. In case of Weiner's original paper, we have it. The bounds coincide. Reversely degraded, we have it, this transmission capacity. Then we have an identification capacity, and we have a common randomness capacity. Those are completely determined. But surprisingly, identification capacity is much bigger than common randomness. I mean, it's second order anyhow, but bigger also. And it has an easy explanation. The common randomness used for identification needs not be secured. Only where you do the square root n trick, this part has to be secured. This way, the identification is secured. And you can use dirty common randomness. That's why you're bigger. So this is, and this, now I come to some part which justifies the title, more the general transfer. Let me tell you, there are three things. What is important for general theory? The questions of the receivers concerning the given ensemble to be answered, like in identification. But there could be other type of questions. The prior knowledge of the receivers about the situation, the prior knowledge of the senders. This has to be built in somehow from the beginning. So whereas until now it was assumed, well, you throw this all away, semantic all the way, and then you do the transmission, and then you have it. But that's not true. And I look at one case where there's one sender answering several questions simultaneously for the receivers. And I call it the general combination of one sender. So we take again the simple discrete memory channel, and okay, this is a code definition. Now here is the model. Nice class of can abstractly be described by a family of partitions. You have a family of partitions of the message set. Decoder is interested in P, wants to know only which member of the partition contains the true message, which is known to the encoder. We describe now some seemingly natural families of partitions. If you take these partitions, consisting out of those simple atoms, that's Shannon theory. If you take a set of partitions having M and non-M, you get identification. Okay, there's several ones in between, but the most challenging problem is general K identification, where you assume now the partition is given by S, M minus S, where S is a set of cardinality K. So in identification, you could say, well, the married people, and one lady gets into an accident. The husbands want to know, did my lady have an accident or not? They don't care which lady it is otherwise, if it's not theirs. That's identification. But it could be that you're concerned about the relative, and you have a bigger group of people you're concerned for. And want to know, is one of them or not one of them? That's K identification, so you can set it all up and so on. And there are, I don't have time to go more into this. There are many, many models like this is interesting, where you want to know the components. You have a vector, and somebody only wants to know component 1, component 2, and so on. If you would transmit, like Shannon would say, the full message, you transmit too much. So once interested in the components, you need, you can do much faster. And there are such phenomena here, many, many. But this K identification is mathematically very interesting, because insofar I was only proving this theorem. So I assume the size of those group of relatives to grow exponential in K, otherwise double exponential. Then there is this characterization of the capacity region. With 2K, it's in the region. With K, it's above. In case of a noiseless channel, they're equal. But the proof involves this very interesting superimposed codes by Kaut-Singleton, which we have never seen in Shannon-type theory used. The question is now open for the general. Now I come to my quantum. So I just draw attention. The quantum people are very much interested in common randomness because they have entanglement, which is something very similar. So there is now this interplay. They call common randomness shared randomness. They have another name for it. So now I come to some methods. The first one is elimination technique, which I use to solve arbitrarily varying channel problem. If you have a random code, by pigeonhole, you know there exists a realization, a deterministic code. We all use it when we prove the coding theorem. But if you have arbitrarily varying channels, you have exponentially many, and you cannot extract one which is good for all of them. That's the problem of arbitrarily varying channels, but there were other ways in which I solved it. I was able to reduce the complexity of the random code, its randomness, by smaller, and then transmitting, etc. And recently, together with Blinowski, we solved it for the quantum channel, the so-called classical quantum channel. So there is a dichotomy, which I established earlier, which says the deterministic capacity is either 0 or it's equal to the random code capacity. And this also extends here to the quantum world. So as I said, recent work with Benoffi. Then there's a covering lemma. I don't want to tell the details. It's a very nice and quick way to prove converse for identification. And it was the only method we could have to prove for quantum channels and identification the converse together with Andreas Winter. Then there's a blowing up technique, which is an isoprometry theorem, which has been invented by the authors here long time ago to do the strong converse for degraded broadcast channels. But in quantum, we don't have such a lemma. You see, methods. We don't have such a method there. So what do? Well, I had another method, a ringing method. If you have two probability distributions on a product space, one dominates the others if you add a factor here. Then you can extract components, not too many, such that conditional on those components, the component-wise probabilities are close to one another. And actually, you could have quite a number of specifications where this is true. This is presently the only method to prove strong converse for transmission. I'm not speaking about identification. For classical quantum multiple extra channels, I did this with Ning Shai. So now I come to source coding very quickly. What is identification source coding? Well, you don't want by all means to know the output of the source. You only want to know, let's suppose you have a code, prefix code, so you have the code words U1 to UN, and somebody wants to know, is it UI, is it UJ? Otherwise, he doesn't care. Like for the channel transmission. If you go along the tree, if you are caring for U1, you look at the first letter. If what has happened starts with 1 and you're 0, you're done already, it's not me. So it's very quick. And it turns out, it is roughly doable always with upper bound 2. So the whole world, of going 0 to infinity, now shrinks to the world 0, 2 in noiseless source coding. And the length of this procedure, so the expected length which it takes to identify, is in close connection to a new quantity, which I call identification entropy, which is written here. And so it plays the same role as Boltzmann-Shannon entropy in Shannon's noiseless coding. There you always get it between entropy and entropy plus 1. Here I always get it entropy and the maximum individual probability. You have to be better than 1, because for 2, interval 2, 1 is a big number. So this is, I don't want to, well, maybe, those are definitions, various criteria for performance, and then we do uniform distributions, Hamming codes. Now, here, Hamming codes, no matter where you put those two leaves, it's always the same performance. In identification, it's more sensitive. So whether you put things here, on the same branch here, on this branch, or whether you take them, this is better. It's more balanced. For Hofmann coding, it's all the same. It doesn't distinguish this. So now I am, okay, so this was a theorem about it. Okay, okay. Now, okay. Now I come to the second part. So there you have it. Beyond information theory. Well, time is passing very fast. Yeah. So updating memory is not so clear. It's changed. You want to change it now clearer. Yes, after you listen, a little bit clearer. You want to change the content. This way, we changed 7 letters. And let's suppose this has a cost, the letter of cost has a cost constraint. How many messages can you store such that you could update from one to the other? This is a diametric theorem. The distance should be less than something, and you maximize this. So those are anti-codes. So this way, you, in a very quick way, you come to anti-codes. And this was studied with Levon Kachatria, and we could reduce it to this Erdős-Corrado problem, which was called an intersection theorem. So you have families of sets in an n set, all have cardinality k. the intersecting T points. And then you take the system of all of those and optimize over them. Erdős-Corrado only could prove if K and T are constant and N is big, then the naive solution is optimal. You fix T points and take all sets containing them. But then people discussed when is the naive optimal. Wilson, several papers. There's a report with 100 papers already 20 years ago. It's the most quoted paper by Erdős. And so here's the solution. Take sets Fi, which have the property, they intersect the interval from 1 to 2 in at least T plus I points. This enforces that two of them intersect in T. And then, making those calculations, we know that MNKT, the optimum is this. And if N is not of this form, it's of this form, we have two solutions, FR and FR. And we have up to isomorphy, permutations of components and letters, all solutions. So we have all solutions. In particular, this proves the so-called 4M conjecture of Erdős-Corrado 38. This is a special case. Ground set has 4M elements. The subsets have 2M elements, exactly half. And they intersect in at least 2. There, the naive solution is not optimal. Better is to take the family of those which intersect 1/2, the left half, in more than n plus 1. Then they mutually intersect in 2. This is bigger than the naive, and we proved this is optimal. And for this special case of our theorem, Erdős paid the highest amount he ever paid after Semerelli. So this is, yes, and we developed new methods of shifting together also with Harut Aydinian, who is here and also gives lecture. You should go to him, he has something to say. Then there's also a local global principle with Schei, which concerns isoperimetric theorem, which is of the kind, if you have the lexicographic order as a solution of an extremal problem for words of length n, for words of length 2, then you have it for all words. It goes from local to global. And this is a central part in the recent book by Harper, Global Methods for Combinatorial Arithmetic Problems, just appeared last year. And using this previous theorem, we also solve the diametric theorem completely all cases, for all alphabets. And it's not always a ball. There are cases where it's a product of ball and cylinder set in a judicial way. Okay. This is another one I proved if you have a group structure. Now, those are papers where you find this work, advances on extremal problems, and so on. Forthcoming book with Blenowski, and there's a book by Erdős. And there's also a book in Springer lecture notes on computer science to appear. Network coding. You all know Shannon's discussed flows, I mentioned before, but he somehow did not study information flows. And let me just, then we proved the theorem with Scheiding 2000 theorem, min-max theorem, which says one source, several things. What you can send from one source to a thing, water for instance, Ford Volkerson answers, min cut max flow, it's a maximum. So for everyone we know what is the maximum. So, but now you want to send simultaneously to all. You cannot send the same water to all of them, but you can send the same information to all of them. And so you take the minimum of the two, of all of them. Of course, you cannot do better, but we prove you also can do this. That's our theorem. Now, if you have two sources, the world is much more complicated, more than one source. Then it's, well, people study it from all kinds of ones. But for me, the interesting part, it is very important for combinatorial extremal theory. And combinatorial extremal is what we're all doing. We optimize. You know? We all optimize. Money, speed, whatever. And it's very important not to say, for me, it's good enough to have a bound or to have it asymptotic. To give exact solution is, in the long run, very important because it gives deeper insight. That's why I think extremal problems ought to be studied. And so it turns out that setting up a certain network, you get all of a sudden those anticodes which I described, so optimal anticodes, as solutions. You get orthogonal Latin squares as solutions. So this area is rich of combinatorial problems. Already the classical had rich connections, but this is even richer. So even the great Lovers gave recently a main talk in Poland on random graphs about this work, because there are connections to other network theorems by now. Okay, and it's even may be that algebraic geometry has to change and so on, because we have the situation that even error-correcting codes come up as optimal solutions in situations without noise. There's no noise, but error-correcting codes become answers. So this is a fascinating area. Now I come to the work with Pinsker. This is the Hamming bound. What is localized errors? You all know what error-correcting code is. Localized errors. The sender a priori knows where the errors may occur. Let's suppose here they occur. But they don't have to occur. And you use this knowledge, and then Pinsker and Gelfand Basaligo solved this problem for the binary, and they proved that it is always the Hamming bound. And for Curie, it was very difficult. And this was the problem we worked in. So there were two positions. My position was, with increase of Q, the Hamming space should become more flexible for packing, because you're not packing balls in this case, you're packing unions of cylinder sets. And I thought it should become more flexible. But Pinsker argued the knowledge of E, where the errors may occur, is less informative if Q increases, which is also true. And the question is, who wins? And the present situation is, we have it after 1/2 it's 0. But we have it for all tau, very close to 1/2. So it is Q divided by Q squared. Yeah? So if Q goes bigger, it goes to 1/2. So this little piece is still missing. There's also no counterexample. That is the present situation on this problem. Now I come to search. Okay, so I use the notation CFQ. This is supremum of rates achievable for tau. I call it capacity error function, a term which has not been used, but it's the best way to express this. And now, here's Berlekam's result, and his key thing was here that you took a tangent from 1/3. On this tangent, this is always optimal. And then you take other tangents, starting from 1/r. And wherever he hits the Hamming bound, it's optimal. And the in-betweens were done by Zigangirov. Now, we did, together with Lebedev, the Curie case, and we could start with a tangent at 1/2. And this was possible. And we got all those tangents. But there's a new method, and I want to say a word of the method. The method is the following. You take your message set. You encode it into the letters from 1 to q minus 1. You don't use the letter 0. And you take block lengths n minus 2t. I call it the skeleton. Now let's suppose, and the 0 is used only for control, only for correction. Let's suppose there's message I, and the image here is this. So the sender tries to send this, the skeleton. Now he starts sending x1 until an error occurs. Two types of errors. You switch within this set. This one type, then the sender sends with smallest possible L possible 2L plus 1 times 0 until the decoder receives L plus 1, 0. Then it interprets the next XP again and continues the algorithm. If an error occurs in the form that you send the letter and goes to the 0, the sender decreases P by 1 and continues, transmits as the next step. Decoding algorithm, the receiver just regards the 0 as a protocol instrument. He erases it with a rubber. He erases it by a rubber, who in addition erases the previous symbol. That's the decoding rule, and this is optimal. I don't have time to discuss this example now. But what happens now if you want to get the other tangents? Then the protocol is not done by 1 0, but you take all zeros which do not contain a block of 2. And then you take those which do not contain a block of 3, and this way you get all the tangents. And this way we also get the Berlekamp case. Because the Berlekamp case is not in here. You see, here, if Q is 2, it's 1. You have only 1. So originally, you don't have it here. So in binary, you could not invent this method. could be invented only for bigger alphabet, and then you go back. Okay, so now we come to Reni. I told you before, here the test sets are restricted to k, and I found the answer. Well, what should be the number of questions? Log n would be the case when you can take all sets, reduced by binary entropy. And previously, for many years, this was best results. They had such a constant. They didn't even have the idea that entropy should rule this. And the reason was, Reni also studied random selection for search. And with random selection, he was worse off by a factor of 2 than by construction. So he said random is no good. Well, the point is you have to use expurgation techniques. But they didn't know in this area, and that's why this area got stuck at that point. Now I come to Gallaghers problem, which you have Slipjan Wolf did correlated source, and he did conditional correlated, so you don't know the distribution of the x's, only the distribution, and asked the same question. And Gallagher said in some cases, this is the answer, the maximum of those conditionals. But in some cases, I don't know what happens. The reason is he used random coding. If you use random coding, what is the problem here? This is not very visible. So you introduce a hypergraph consisting in edgewise of the carriers of the conditional probabilities. And the small ones, colored at random, is very bad. So I do combined, greedy, random selection. And this does the job, and this is already in my 78, 79 paper. So further perspectives, protocol information is very important. There was a paper by Gallagher on protocol which didn't go from the ground. I think it's a mistake. People should look at it again. Because in the problem of the search, you know, the zero used as protocol is very important. This ought to be better understood, protocol information. And also in the work with Pinsker, where you have the error patterns E, you may just transmit this to the receiver. But that's very bad. So what better can you do? Well, you cover all sets of cardinality T by sets which are bigger, and the best choice is cardinality Q divided by Q minus 1T. This is the best protocol information. So there also this issue comes up. Okay, this is as a concept of solution. Let's suppose you have a polynomial, you divide the unit, the line into intervals, and somebody only wants to know whether in this interval I plus 1 there's a root or not. Somebody else G or J plus 1. There must be one protocol which gives everybody his answer with probability close to 1 correctly. So this is a concept of solution now, not just having to do with communication and so on. It's a concept of solution in mathematics, but only works if you allow probabilistic procedures. Otherwise, there's nothing new. Yes, so here is, I mentioned tau. You know, Tau Green did this famous theorem, the arbitrary long arithmetic progressions in the primes. And now he recently wrote a note where he said we can do the semi-ready regularity lemma, which was a graph theoretic theorem, probabilistically using conditional expectations, and then he realized the connection to conditional mutual information. So this way information theorem, I improved just the constant, this is the best constant. And this is, I lectured on it, so maybe it's good for information theory to follow this up, this connection to combinatorics and number theory. So what is the question to Shannon? In his paper on two-way channels, he wrote, the independence required would also occur if the transmission and repetition points at each end were at different places with no direct cross-communication. Now, I understood this as being a statement about the interfering channel, but already very early I showed that this is not optimal, and I give an example. So it's not clear what he had in mind. I asked Shannon's attorneys, one of them unfortunately is not here today. I asked him 10 years ago, he gave me different answers, none were satisfactory, and he had to accept that they are not satisfactory. So what did Shannon have in mind there? The other one is one which Tom Coburn also often quoted. Thus we may have knowledge of the past, but cannot control it. We make it through the future, but have no knowledge of it. Now, I was motivated by creating order, by the Maxwell-Damon thing, and by Clausius's work. Clausius was the person who stated the second law of thermodynamics, and he also introduced entropy. Here he is. This is from the Encyclopedia Britannica, newest edition. And here's a statement of the thermodynamics. Heat cannot of itself pass from a colder to hotter body, stressing the concept of entropy. He also had a molecular approach in other areas, electrodissociation. So he was a very bright chap. And now here is entropy. This was solely Boltzmann. This was solely Shannon. This is also called Shannon Entropy. And as Reni remarked, that is unfair towards Boltzmann. And this is my identification entropy. And here's this quote from Reni from his book, where he discusses this quantity. And Boltzmann was the first. And it would even be proper to call, so it may be considered as a pioneer of information theory. It would even be proper to call the formula the Boltzmann-Shannon formula. And I share this view, and I think it's important. Since we communicate more with physicists, we must use the same language because they call it Boltzmann entropy. This community calls it Shannon entropy. We ought to have one language. Otherwise, things run away, like algebraic coding runs now to the computer people, as we have heard in Wadi's talk. Yeah? So it's very important to think about those things. So, and then this is a theory of creating order, and this is my last thing. I'm at the end. So there is a string of things coming here. Yeah, it's coming. Gold, silver, platinum, whatever. And there is a box, and you have a certain number in the box, and all the person at the box can do, if one comes in, kick one out. So change or kick one out. And he has two things. He can look in the future by phi and remembers the past by pi. Depending on that, how much can he reduce the complexity, if it's a stochastic process, the entropy, or combinatorial, just the number of strings. That's the compression, and we solved it in several cases with some co-authors. I have no time to go into it. It's a whole area. So those are the two papers, 89. There are at most 20 follow-up papers, at most. And I think it's a pity, because this is a general way of looking at the Maxwell problem, where you have gas with fast particles and slow particles. But you don't need all the mechanics and all this. It's a general question. We have some knowledge about the system, and we have some space of operations. How can we perform things optimally? And why does it not work anymore? Oh, it's the end. Thank you.
There will be some announcements by the organizers, but perhaps we have time for just one or two questions. Chris.
Too big a question. Well, let me say this. I'm very much interested. I always was a great admirer of Charles Darwin, before this big boom started. And always wondered about such things. And I'm looking still for applications of identification even though I don't care for if a good theory is a good theory. I am not too much application-oriented. But all people could do is alarm systems. For alarm systems, it seems to be useful, very well. We had a big meeting on animal communication in our university. And there were many, many experts, and some of the things smelled to me like it is useful for communication there, but we didn't find it. But I would also say we don't find it because the biologists don't ask such questions, because they don't know theory of identification. You see, to ask the right question, it takes both theory and practice. And they lack the theory. But as I hinted at, noise may help. This gives me, in case of feedback, yes, this gives me the idea that those things may be relevant in evolutionary process and in biology in general. So one should keep a close look on those things. That's all I can say at the moment. But it's a very central question.
Let's once again thank the Shannon lecturer.
Still one comment. If I didn't completely fail, let me say why. I told you in the beginning, I have to fail with probability 1. So in case I didn't fail, I give you the answer of the secret. There's a philosopher, I think he lived in Poland, Reichenbach, who once summarized the content of Shakespeare's Hamlet. The only question there is, what is the difference between a probability which occurs for sure and one which occurs with probability 1? So if I didn't fail, it's because I didn't have to fail for sure, only with probability 1.